All right. So some new material, we're starting sort of new material, but we really have to review old material first because we really want to understand pole zero maps because a lot of what we're going to be doing this semester is looking at pole zero maps and looking at performance. So again, as an engineer, we're trying to design systems. And so by understanding the performance of a system, and then making some design assumptions about it, we'll be able to pick points based on here's what I want my system to perform to. So here's how I'm going to specify the design. And in the Laplace, that's not real, right? It's just some complex frequency domain. But we want to be able to go ahead and interpret what is in the Laplace domain and how does that correspond to what we do know, which is in the time domain. So we're going to spend a little bit of time coming up with sort of the corollaries or the interesting things about in the Laplace domain, how we can compare those to the time domain. And then we'll set some parameters, which are actual specifications that you would find if you were on an industry. So with that, thank you for your folks that have got your cameras on. It's always great to see smiling faces. Not a lot of smiles from the in-class people, but maybe we can get a couple. Tell some jokes. I heard a joke the other day. It's not appropriate, but it was pretty funny. It was clever, but it was inappropriate. So I won't share it on. No, it was just one of those things where you have to have the right group of people. But anyway, it wasn't racist at all. Don't worry about that. It wasn't even sexist. It was just a stupid joke that I can't tell my kids. So with that being said, before I get myself into more trouble, let's talk about time response. So again, we write mathematical expressions with ordinary differential equations, and that's what our system is representing in the real world. But the real world math is very complicated. So we do Laplace to make the real world a lot easier to work with. But we're no longer in the real world, we're in the Laplace domain, essentially. So that's why we talk about transfer functions. And if we look at transfer functions and we study them, we might be able to figure out what's happening from a transient response, time response, and a steady state response just by viewing the transfer function, right? Kind of just the introduction that we had today. And if we system is modeled or set, then we can look at it and say, is our system going to give us the behavior we want? And if not, we might need to make some changes. All right, so what is the worst case real world input that you would find for a real world system? If you had to think about it. In the real world, right? If you're telling your car you want to speed up or slow down, what do? You depress the accelerator, right? You put the accelerator down and then you go until you get to the desired speed. Does anybody here jump on the accelerator and put it to the floor? Maybe if you want to see the performance or whatever. Most people don't, right? You try to gradually increase speed, but that dumping the accelerator and putting it to the floor is essentially a pretty serious transient on the engine, right? It's a pretty big hit because now all of a sudden you're dumping all this fuel and then the car has to downshift and yada, yada, yada. So it's harder for the system than just doing that gradual increase. It's the same thing in the process control, or when we look at real world systems, what's the worst case scenario is when you have a very rapid change from what you currently have to what you'd like in the future. And for math, it's really easy for us to say, what about an instantaneous change? I want this, I'm at this level, and then I instantaneously want to go to this level. If you do that in the time domain, you have something that looks like this, correct? This is a step input, isn't it? So one of the best ways to determine or assess if a system is going to operate is really work it hard. You input it with a step input to see, is that system going to respond the way I want it to? And another term that a lot of control systems engineers use, it's called a bump test. Why do you think it's called the bump test? Let's say you have, sorry for those of you in TV land, but I'm going to stack up a couple cans on a corner of a desk. All right, is this a stable system? For TV land, I'll try to show you. It'll be upside down. I got 3 soda cans on top of each other. Is that system stable? Cans aren't falling, right? How would I simulate an input that is a unit step? Whack it down? That's pretty obvious, right? What's going to happen is the end result. How about if I come to the system and then I just I bump it? Still stable, right? How many cans can we add? Maybe we should do this for a while if you want to have fun.
You have a lot of trust in something that still has,
That one does not. Well, 4 cans. That a stable system? TV land, you can take a look. Hopefully you can see. Can you see? I don't know if you can see. Can you see
Yeah,
the
we can
cans
see it.
upside down?
Yep.
All right. Now, if we bump it, let's stay up. Okay, right? So the concept of a bump test is exactly that. It's perturbation. It's a change in the system, a bump. The system changes, and then eventually, what you end up having is the system is no longer stable. We would call that LIBO stable. Remember that term? Bounded input, bounded output. And the definition of stability is we want our cans to be standing in an upright position. Clearly, they were not when we got to 4 cans. So our tests, our bumping it, would not necessarily be a stable result. Now, you can do all these other ones, impulse, ramp, or sinusoidal, and it depends on the application. Sometimes you want to have an impulse function, which is just a quick, like when I actually bump the table. Normally with an actual bump test, you bump it and then you keep it moving at that very fast rate. So it's almost like we would keep the table moving at that fast rate. Impulse functions are really hard to find in the real world. They don't really exist. So normally a step function is what we would typically do. And so using this, the step function really tells us a lot about how that system is going to perform. And if we have a very complicated system, if we prescribe a bump test to it, so we set the system at a stable operating point. Let's just say we have an input at 10%. And then everything is stable. So nothing is changing. All the levels are changing, are stagnant. The speeds are stagnant, nothing's changed. And then all of a sudden you hit it with a 5% or a 10% change. Now you can monitor the output of the system as levels change. They go up and down, or maybe they increase a little bit. And on and on and on. So now you have a bunch of monitored parameters, and then you can take that, and we talked about this early in the semester, you can take those monitored parameters, bring it back into Excel, and then remember how we did our equations, where we could do a first order equation, second order equation, to come up with a representation of the system. In the real world, they do that. They have things called ProTuner, as a software package with a little box that you can go ahead and inject test signals on, and then you can monitor the output or record them and then see how the system responds. So if you have a complicated system that you don't want to spend a lot of money for an engineer to go ahead and determine what the actual block diagram needs to be, you can do a bump test and that works perfectly fine. So how does this apply to us? Because we're going to use these two, the steady state response and the transient response. Do you remember what we talked about on the exam? What's a representation of the steady state response, or how do you find it? Final value theorem, right? Because the final value theorem tells us what the final value is going to be in the time domain, all using Laplace domain. So I can get the steady state response by doing the final value theorem and staying in the Laplace domain. How about the transient response? Can I get that? Transient response is another way to say what? Steady state means the output is forced to do something. What about the transient response? What does that mean? When I say something's transient, it's short term, right? It's going to go away. So in the time domain, it has an e to the minus t, right? Multiplier in it. So if you look over here, this is the transient response. How does this look like in the Laplace domain? It's something over S plus A, right? This right here, because it has an S plus A term, that means it's going to decay away to zero. That's a transient. Or it could be right? That could be in the denominator. As long as there's an S plus A, then we can have that. This here is always a real number. So if I'm trying to draw my pole zero maps, anything that has a pole that is in that left-hand half plane has to have a real part, right? Because remember, this is the real axis. So as long as you're to the left of your j omega axis, you're going to have a real component. And that's going to be transient. What about steady state? Anything that's on the j omega axis. Why? Because if we did final value theorem, if it's going to be a steady state value, we know it's got a 1 over s term in it, doesn't it? Or it has a 1 over s plus omega squared, s plus omega squared term. What's the difference between these two? There's no real part in the case where there's no decaying part, right? It's a steady state part. I mean, a steady state, which means there's no decaying exponential. So there's no real root that's associated with that. Okay. So again, just looking at that, we can look at the transfer function, and I can tell you what the transient response will be. And I can also tell you what the steady state response is going to be. But I need to know what the input is for the steady state response, right? I need to know, because in real world systems, energy doesn't just live forever, right? We don't just have something that if you energize it once, it stays on for forever. It just doesn't happen that way. So usually a steady state response is going to come from the input and not from the actual transfer function. So just to respond with a different term, steady state and decaying or transient, you can call this transient if you don't like decaying. Other terms you'll see are forced response, right? Because it makes sense. If I'm providing an input source of energy, I'm forcing it to do something. Whereas natural response is I energize the system doesn't like to change. So it's going to put up a little bit of a fight, but over time, it's going to back off, right? It's going to go ahead and just be like, all right, well, I can't keep fighting you. So at some point, I'm going to go ahead and roll to a new value. And the combination of those two is the output response. It's inclusive of the natural and the forced response. The poles of the transfer function, which is another way to say any of the roots in the denominator, those are what force my transfer function. So my g of s is going to be equal to that. That's going to force that to infinity. When you evaluate at a pole, it forces it to infinity. That is going to be our poles here. In the numerator, those are our zeros. And they force our transfer function to go to zero. That's why we call them zeros. Poles is not obvious. I don't know why they came up with the term. Maybe it sounds like they should have called them infinities or something like that. It might have been a better term, but
I did look that up.
So we're not going to go ahead, Rita.
I looked up why they were called poles.
Go ahead.
And it's because on an XYZ coordinate plane, when you look at it in the 3D dimensions, the poles, because they go into infinity, they spike up all the way up. And they look like two poles sitting on a 3D map.
Oh, wow. Okay. I'd never seen a 3D. Thank you. That's, see, you got to love, is that Wikipedia?
Chat GPT.
Oh, ChatGPT, even better. Thank you. All right, so let's take a look at a really simple block diagram. And we have a pretty simple transfer function for our system, s plus 2 over s plus 5. Now, looking just at that system, I can see that I have zeros at -2 and poles at -5, right? Because those are the roots of the numerator and the denominator. The question I have for you, are there any other roots and poles that I don't see? Any ones at infinity? Remember we talk about infinities, right? Do we have any poles or zeros at s equals infinity? We get Avery saying no. Anybody else say no? Anybody say yes? Anybody say I don't know? You don't know or you know? What's the rule about poles and zeros?
You have to have the same number of them.
Yeah, Rita just said it perfectly, but Avery was on the right track. You have the same number of poles as zeros. So do I have the same number of poles and zeros? Sure, one each. So I don't have any unknown poles and zeros or any poles and zeros at s equal infinity. They're going to be the same. So I only have those two. And what that tells me is I know just by looking at this system what the transient response is going to be. What's the transient response? It's going to be e to the -5t, right? We know that the transient response is going to come from here. What about the output, the forced response? Where does the forced response come from? The input, right? This is what the system is eventually going to go to. So I can't look at the transfer function and tell you the forced response. I can only tell you the transfer, the transient response. And so to actually get what the output is going to be, which again is the transient response plus the steady state or the forced response, I have to actually apply an input. So I'm not looking at G of S, I'm looking at C of S. And C of S, I want to do partial fraction expansion on because I want to go back to the time domain and see what the results are. Am I right on these two? Anybody want to check my work? Did I get those right? Those correct? Yes, no? Yeah, because you see, if I plug in S equals 0 over here, those go bye-bye. And then this becomes -5 plus 2 over -5, which is equal to -3 over -5, which is 3/5, right? Those two cancel each other out. So in my partially factored form, where I'm ready to go back into the time domain, here's my expression. And then I go back into the time domain and I can see here's my result. Here's my forced response. And here is my transient response. Notice S plus 2. Does that show up at all in the output? Do you see e to the -2t in there? Not at all. It does have an impact on the output because if I made this S plus 1, I would get different results. But because it's S plus 2, I'm going to only affect these coefficients here. I have no impact on the characteristic behavior. How that waveform decays over time has nothing to do with the S plus 2. It only has to do with the S plus 5 term. So we plot the poles and zeros. We can see, let me slide this up over here. We have a 0 at S equals -2, and we have a pole at S equals 0. All right. Questions on pole zeros and pole zero maps? We've seen a lot of pole zero stuff and pole zero maps, but we're going to go back through it in a lot of detail just because we're going to see what happens when we change things. So that's a good question. What happens if I move that to the left? Does anything happen? let's say we move it over here. What happens? Well, now our C of S becomes S plus 4, not S plus 2, over S plus, or S plus 5 times S. I'll give you 2 minutes. Give me A and B. You all should be able to do that in 2 minutes, right? Time's up. Got it? Was that not 2 minutes? Who's got the answer? Go ahead, anybody. Very good. So 4/5 S plus 1/5. Did the transient behavior change at all? There's still 1 over S here and a 1 over S plus 5, right? So that doesn't change what our Laplace table looks like. Just my coefficients changed. That's it. So changing the locations of the zeros only changes those coefficients. So we hardly ever change those because it really doesn't move the characteristic of what we want. What if we took this and moved it over -3? I'll give you 2 minutes. Give me the final answer for C of S. So let's go back to the original. Let's have a pole that's here. So this is pole 1. And this is 0, 1. So we won't have it moved over. We'll just use the original one. So look, we just want to see when we change things, what happens. We know how to do partial fraction expansion really well. Great. Let's see if we can take the next step. What happened? You all were so confident before. What changed? Pardon? Anybody struggling with the translation from the graph? You have a pole 0 map, right? Excuse me. You have a pole 0 map. Can you not go to the transfer function? We still have 1 over S, right? That's the input. Isn't it S minus the 0 over S minus the pole? This is -3. So to go back to our transfer function, it's S minus the -3, becomes S plus 3. And the 0 is S minus the -2. So that's 1 over S times S plus 2 over S plus 3, which when we do partial fraction expansion, we end up with, let's see if I can do this in my head. A is going to be equal to, let's see, where is my, so A is going to be equal to 2/3, 1 over S, and then B is going to be equal to, let's see, correct? Does anybody else get that? Positive 1/3, sorry. What's changed now? This is exactly the same as before, but this has changed. This was e to the minus 5t. Now it's e to the minus 3t. So my characteristic is going to look very different. Instead of doing something like, let's see, e to the minus 5t, so we reach a steady state faster, it's going to look like this, right? It's going to have the same basic shape, but it's going to take longer to get to that stable point. Okay? So again, changing the zeros doesn't really change the characteristic. Changing the poles does. What about this pole right here? Can I change that? I could, but I probably wouldn't, because this is the input pole. So in reality, I really don't care about the input pole, because it doesn't really affect the behavior of it, other than just knowing what the force response is going to be. So oftentimes you do a pole zero map, you can neglect the input. Doesn't really give you any information. All right, let's see if I did most of the stuff. We talked about bounded input, bounded output, right? Which is if the input is bounded, the output will be bounded if it's a bistable system. We don't show the input to the system because it doesn't really affect the stability. Why does it affect the stability? Because if it's a bounded input, your system should be bounded output if it's stable. If the input is unstable, then all bets are off, right? You can't, who cares if the system is stable? You're just going to keep dumping energy until the system explodes. What about the poles that are on the j omega axis? They have no decaying exponential, right? So is that going to necessarily be a stable system if I have poles there? Is it going to be bistable? The answer is maybe. Because if I have a pole, a system pole over here, that's the same thing as 1 over s, isn't it? What is division by s equivalent to? Division by s in the Laplace domain equivalent to in the time domain? Louder? Yeah, you're taking the integral of something, right? What if I integrate a DC input? What's going to happen eventually? It's just going to keep increasing until it goes to infinity, right? So this one is, if I hit this with a unit step or a DC input, it's unstable. Everything else, it's stable. So is this a bistable system? Maybe. It's bistable all cases unless you put it with a DC input. And you can tell that because here's my transfer function. I hit it with a unit step. That becomes 1 over s squared, which looks like t in the time domain, right? As time increases, that just continues to go up and up and up and up and up until it blows up. What about over here? Those two. We know that those are going to look like s plus omega squared, right? If I hit that with a DC input, that's going to have an a over s plus b at an angle of theta, right? Are those stable systems? Do you see anything going to infinity? Because this is going to go to DC. So this is a unit step. And this right here is a sine wave, right? So it's a DC. Essentially what you get is something that rings up like this. It doesn't blow to infinity. It stays constant. Here's the other thing. What if I take the input and I hit it with an input signal that's a sine wave as well at exactly the same frequency? That becomes t sine of omega t. Why is that an issue? Because as time increases, my sine wave starts like this, then gets bigger, and then eventually will blow to infinity. What is this concept right here? Resonance, right? Natural frequencies. Anybody here into music? How do you tune your guitar or musical instrument that you play? You have an app? You new techies make it so hard. You can hear it because you've been playing for a while, right? How did you first started doing it? Imagine you took your iPhone and threw it in the trash. Tune it off a string you know, but you have to know if that string's in tune, right? Anybody know what a tuning fork is? A pitch what? Pitch pipe? I've never heard that one. I've always heard them called tuning forks. What is a tuning fork? How does it work? You bump it, right? Boink. Then you sit there and you listen to it and it oscillates at whatever frequency it's set at, right? And it oscillates for quite a while. You just do a little tap. What happens if you could tap it at the same frequency that it's vibrating at? It would get louder and louder and louder and louder and louder until it breaks. So if you could adjust it hit it at the same time, you would eventually break it. Any other analogies to that? Caps and inductors is one. So you know what a resonant circuit is? Did John talk about that in circuits class? It's when you have a circuit that only has an inductor and a capacitor. You energize the system once, and then the capacitor and the inductor just share energy forever, right? Yeah, if you have an inductor and capacitor circuit and you energize it, where does the energy get dissipated? Yeah, it just goes back and forth. It doesn't get dissipated, it gets shared. So in a pure resonant circuit, that's what happens. That's why have you done op-amp circuits where you've done they call them Chevy or Butterworth filter, where you're doing passband or reject filter. You have a very high or very low impedance at a certain frequency, so it allows all that frequency or rejects all that frequency at the value. But then it allows or rejects every other frequency. So that's a filter application where you're trying to tune it. So you use those concepts of resonance. I want lots and lots of gain in my system, or I want no gain in the system if I want to reject it. Any other applications? Going back to the music world. I don't see this all that often, but you can take a look on YouTube. You ever seen an opera singer sing to a glass? The what? Sure, they're holding the glass, right? Or maybe it's on a table, and they just sit there, and if you notice, this opera singer sings at a very specific frequency, right? It stays at that frequency, and then you'll see the glass start to vibrate. And then what ends up happening? Eventually the glass breaks. I think it's only for female opera singers. Anybody know why? I don't think a male opera singer can do it, maybe, but I haven't seen it. Because female opera singers have a higher range, right? So to oscillate that piece of glass at its natural frequency, you need to have, most of the time, you need to hit a higher frequency. And I'm not saying male opera singers can't do it, but they tend to have lower range. So they can't hit those same frequencies. So if you had a male opera singer, even if the male opera singer can sing at perhaps a louder volume, they wouldn't be able to break the glass because they can't get it to vibrate. So that's the concept of natural oscillation frequency. Remember back in your physics class, the Tacoma Narrows Bridge? Why'd that break? You could see it vibrating like this, not vibrating, but swaying. Another way to see it swaying, it's oscillating back and forth. It broke because, however, the wind was accelerating the bridge so that it was just at its resonant frequency, and it just got higher and higher and higher until the bridge eventually broke. And so knowing the resonant frequency of things is really important, because if you excite it at its natural frequency, like buildings, you can actually have building collapse. It doesn't happen all that often, but it can happen. On my time, plenty of time. Okay. So let's move this over here. So here how it shows what we've talked about in that last slide. How we have 3 parts to our system. We have an input pole, right? We have a system 0 and a system pole. By the way, did I upload this presentation to Brightspace? Is this one on Brightspace? Anybody know? Did I upload it? I might have forgotten to do it because with the tests and the skip day. If I don't have it out, I thought I did, but I may have forgotten. So if not, I'll upload it when we get done with class. So here's an input pole, right? We can see this is the pole 0 map for the input pole. It's just 1 over S. Again, not really useful, but what's more useful is you can directly translate how that correlates first off into the Laplace domain value, right? Or the Laplace domain part of the function, which is 2/5 over S. Not the 2/5 part, just the S part. The input only has an impact on the pole at S equals 0. And when we do our partial fraction expansion, what's going to be the forced or steady state response? What about the 0? Well, the 0, what we just saw, is it has no impact on any of those poles. It only affects the zeros, which means it's going to impact our coefficients. So there's no impact by monkeying around with the zeros other than changing the coefficients. That's all it does. And then finally, our actual pole for our system is only going to impact our pole there, and that becomes our transient system. All right. So you can see how each of those get modeled not only into the pole 0 map, but then how it gets modeled into the time domain. 2/5 unit step only exists because we force it with a unit step input. E to the minus 5t only exists because we have a pole at S equals -5. The 2/5 and the 3/5 exist because of the S plus 2 in our original transfer function. By the way, where is my unit step for my input pole? Does it exist? Remember, we said that this shows up over here. Why don't I apparently see it in the output time response? Yes, sir. No, the input pole has a forced response, right? So it does impact the output. But do you see the 1 over S term that you get from the input? It's not obvious, but that's 2/5. Isn't it really 2/5 times U of t, right, for my unit step? We just write it as 2/5. We don't write the U of t, but mathematically, if you wanted to be 100% accurate about it, you would say 2/5 times the unit step. Okay, so that's where that term comes over here. So you can see coefficient, that comes from the zeros. That comes from the first pole. That comes from the second pole. And you can hopefully see how you walk through and you get your systems to respond the way you expect them to. So this is just a summary. Input function, that's going to be an input pole, right? Not an actual system pole, but an input pole. And that is going to give me my forced response. If there is one, you could have an input of a decaying exponential or an impulse function. Those go away. So it's possible that you have no forced response. Your system poles, well, we don't really have an intermediary stage. So those determine the natural response. And my system poles and zeros ultimately affect amplitudes. If you notice in the previous slides, we didn't really talk about the poles affecting the amplitude, but they will if you monkey with them, but they have a bigger deal affecting the response. So the system poles and zeros, why my throat so dry, really is going to affect amplitude zone. So just kind of a quick summary way of going ahead and describing. So here's our pole 0 map for the 10th time, right? What does LHP stand for again? Left-hand plane. Very good, Avery. What does RHP stand for? Right-hand plane. I'll only add this because some people do it slightly differently. What does LHHP and RHHP stand for? Yeah, some people like to see the left hand, then half plane. Oops. And this is the right hand. Half plane. So that's the left and the right of my pole zero map. But there's one other part that we didn't include in the pole zero map, and that is the J omega axis. J omega axis does not exist in the left nor in the right. So that's why we talk about planes and the J omega axis. Everything in the left-hand plane or the left-hand half plane, everything, and when I mean everything, all poles in LHHP system stable. So I should, oh, go ahead. Well, we'll get to that in a second. All system poles, right? Not input poles. Why don't I care about input poles? Because if the input is in the right-hand half plane, then it's an unstable system to begin with. If it's on the J omega axis, it doesn't matter either because it's just a unit step and it doesn't affect the stability. So all the system poles have to be in the left-hand half plane for it to be bibo stable. Over here, not all. What's the opposite? Not truly the opposite, but what is another case of not having all poles in the left-hand half plane? Any pole. So if all poles are not in the right half plane, then you could say any pole in the RHHP is bibo unstable. Okay. And then the J omega axis, it could be stable or it could be unstable. Because of that, we call it its marginal stability. So we don't say it's stable or it's unstable because we're not sure. We need to do a little bit more investigation to see, yes, it really is stable, or no, it's not, because it depends on the input. Remember what we just talked about? Take a unit step and run it to an integrator. Eventually, it's going to be unstable. Do the same thing for exciting something at its natural frequency. We're going to have an unstable system. So these three are sort of the summary of talking about stability and defining stability. It would be pretty important to make sure you see and understand where each of these terms come from, because it's going to help a lot when we start looking at root locus plots, and maybe even, well, I don't know if we do Bode plots, if it really applies, but by looking at our pole zero maps and then denoting these, we can actually do it. Because again, we're going to start monkeying around. We're going to be moving poles to the left, to the right, and see what happens. And we're only really going to move poles, not zeros. All right. So poles can be complex, but they don't have to be. Meaning I can have all my poles here on the real axis. All right. If I don't have all my poles on the real axis, how many poles will I have that are complex? Pardon? Not necessarily. Yeah, I know that I'm always going to have two, at least two, or an even number. 2, 4, 6, 8, etc., etc. They have to be complex conjugates. Anybody want to guess as to why? Let's see if we got our thinking caps on. You all know the answer. How do I find the poles of a system that, how do I end up with poles in general? What formula do I use to find the poles? Yeah, they both said it correctly. They said it slightly differently. When you complete the square, you're basically monkeying with the quadratic equation, right? Because when you do the quadratic equation, how do I end up with complex poles? What has to be the case when I look at the quadratic equation? Keep going. Hard. Negative b plus, oh, minus 4ac all over 2a. So how do I end up with a complex root? The only way to end up with a complex root is when I end up with a square root of a negative number, right? So that means I have to have a j term here. And if I have a j term over here, what have I just effectively done? Right? It no longer becomes b squared minus 4ac. It becomes 4ac minus b squared. So the reason why I have a complex conjugate is because I have a plus here and a minus here, right? I have to have two. Because if it's complex, that means that under this over here is a non-zero number. Doesn't that mean by definition, when I do the quadratic equation, negative b plus j, whatever that number it is, and then negative b minus j, whatever that number is, right? So if I have complex numbers, that means what under that square root term is not zero, and it's a negative number. So I darn well better make sure that I have a plus and a minus. So that's the reason why you have to have complex conjugates. So if you ever come to a pole zero map, maybe that's a good test question. And I say, go ahead and do the transfer function for this. You darn well better know the answer has S. Let's say that this is alpha and this is beta. So even though I don't show that pole over here, you know it has to be a complex conjugate. So maybe that would be a really good test question, right? Which is there anything missing from this pole zero map? Or would that be too tricky?
They always have
The inverse? How about we just call it, how do we just call it what it is? There always are complex conjugates of each other, right? You have to have complex conjugates of your poles. Okay, whenever they're complex, you have to have a complex conjugate of it. Okay. Let's do a simple problem here. And it's not that simple. But I would do this in MATLAB. Over here, you could certainly do the quadratic equation. Does anybody here from your previous math experience, do you know how to find roots of a third order system, third order or higher system? I don't know how to do that either. It's hard. Yeah, I don't know. I mean, it's been many, many years. I know for second order system, it's quadratic equation. That's pretty straightforward. But I've never seen because it's just trial and error, right? All right, let's try -1. Let's try -2. Let's try 1.5. Let's try this. There probably is a mathematical way to do it, but it's such a cumbersome process that you just use MATLAB. So if I want to go ahead and find the poles and zeros of this, remember how to do that in MATLAB? Anybody want to see it again or? Yes, no?
Yes, please.
Okay. All right, let's see where MATLAB is. So there's a couple ways to do it. So the way that MATLAB wants you to do it, you have a function call in MATLAB called roots. And whenever you do a function call, you have to open it with parentheses. MATLAB will need a variable or an array, I should say, that has the coefficients of whatever you're trying to solve for. So the coefficients are as squared plus bs plus c, and then you just equate those terms. So this is S to the 1, and technically this is S to the 0. So you do it with your coefficients that way. So in MATLAB, I have 2s squared minus 2s minus 4. So I'm going to type the roots. Well, actually, we could do it a bunch of different ways. We can call it an array that has 2, negative 2, and minus 4. Right, do I have that right? No. Okay. So that's our array. Whoops, this is minus 4, not positive 4. Let's double check that. Yep. So now I can do it 2 ways. If you want, you can define a variable, and then you can just do roots of A, and it'll spit out the roots. Or if you don't want that extra step, you can put an inline array 2, minus 2, minus 4, and put the, you get the same result. So either way it works. All right. So doing that here, you end up with minus 1 and minus 2. Minus 1 and 2. What did I say? Minus 2. And then the other ones, you're going to end up with negative 3, minus 1 plus j, and minus 1 minus j. Notice the complex conjugates of each other. So here's the thing. If I want to write these factored out in expanded form, it's s minus the 0. So it's s minus the minus 1 times s minus the 2, right? So you subtract the root. And why is that? Because if I plug in s equals 2 over here, you can see how that goes to 0, doesn't it? 2 minus 2 is equal to 0. Over here, there's 2 ways to do it. S minus minus 3, S minus minus 1 plus J, S minus minus 1 minus J. That's if you want to do pole 0 maps. Go ahead, Noah. I don't believe so, no. Your TIs, but they don't call it factor. They call it, I think in TIs, they call it C-solve or solve, right?
Yeah, it's C poly roots.
Say that again.
C poly roots.
C poly roots. And yours is factor? Okay. It used to be in the TI 89s. They used to call it solve. So you would do solve and set it equal to 0? Okay. Typing factor. Okay. Yeah, I don't think, let's try it. Let's see if MATLAB has it. I don't believe they do. If it gives us an error. Yeah, no. We don't want a simple sieve approach, right? So this is the prime factors of n. So we don't want the prime factors, the prime numbers, but no prime numbers are. So yeah, this is not, well, let's try it. Let's try factor of 2 minus 2 minus 4. Nope. Doesn't work that way. So in MATLAB, I guess they expect you to have a little bit more understanding and go ahead and do it that way. If you want to use that, that's fine. You'd rather use a calculator? Sure. This is okay for doing pole 0 maps. What is it not good at? Something we harken back to last semester. What did we do last semester when we had complex roots? S minus the real part squared plus the imaginary part. squared, right? Because if I look at the Laplace table, this is going to be a sine or a cosine function, right? With a complex exponential. What is this going to be in the time domain? E to the minus t times -1 plus j. That exists in the real world? Can you go build me a function generator or a sine wave or whatever source that has a -1 plus the complex exponential? Can't do it, right? This number is not real. So that's why we don't like it when we have numbers that have j terms in the time domain, because they don't physically exist. This one over here is s plus 1 squared plus 1 squared, which corresponds to e to the minus t, either the sine or the cosine of 1t. Shouldn't even say omega. Right? Can you build me a device that can produce that? Might not be easy to build it, but you certainly can. All right, so we have our factored form here. Now let's do our pole zero map. Oops, where am I going? Sorry, I'm bouncing around. Here's our pole zero map, and here's the script. If you want to, see if you can do that in your fancy Nancy calculator. I can actually do a pole zero plot in MATLAB, and I don't need to do factor and all that stuff. I just have to specify the numerator and denominator, and then do the transfer function block. Now, if you want to do this in MATLAB, you can do it, but here's the thing. You have to have, let's see what the add-ins are, or add-ons, sorry. You have to have, I believe you have to have a control systems toolbox included in MATLAB. So let's see if we can see that here. Right here. If you don't have that toolbox added in to your base version of MATLAB, then you cannot use the transfer function block. It doesn't exist. All right. So what I'm going to show you only works because of this. So the first thing I'm going to do, I'll just do CLS. Oops. And CLC. So I've got no variables. Now I'm going to do my numerator transfer function. So let's move this down over here. My numerator is going to be equal to 2, -2, and -4. My denominator is going to be equal to, let's see what my terms are, 1586. Okay, does that look like my original transfer function? Looks okay, right? Now I'm going to do my transfer function. So here's where I'm going to define a system that has a transfer function with my numerator and my denominator. And watch when I run this, watch what's going to display. It actually gives me the transfer function that I originally created. It's not a sexy transfer function, right? It's got S with a caret in there or two. So I wouldn't say it's how you'd exactly draw it on paper and pencil, but it is the transfer function, isn't it? And so now I can use my pole zero map function of my system to build a plot. So PZ map, and it's going to build, once it's ready to, it'll build the pole zero map of the system. So if you want to check your homeworks or whatever, perfectly fine. You can check your results. I don't think your TIs can do that. Noah's gonna try. He's got a thumbs up.
I know, I was gonna say, I know, I was like a $30 program.
So you do have it?
Yeah, I just.
1586 is the denominator. So you actually have it built in, or you had to add on so you found it for free, or was it $30? Oh,
But I got my first year, so pay it off.
what is it? It's like an engineering work tool or workbook, or? So if you have that's a TI Inspire. So if you have the TI Inspire, you can actually get additional modules, I guess, that can do it. There you go. Or you can download it for free from the university website. So that $30 is going to buy you 12 pack of beer. Is that what a 12 pack of beer costs today? What does the average student in this class drink? So I don't know. I haven't had any alcohol in 7 years, so I don't buy that stuff anymore. What's that? I couldn't afford it. You go to a bar and it's $10 for a beer, plus you got to give a tip, and $7 a beer. That's it. 350. You going to those private clubs? Where? The poorhouse? Oh, that's a nicer, they jazzed it up a little bit, right? Oh, nice. It's a small facility. I can't imagine, like, your eardrums must be blown out when you leave there, because it's. Oh. I know they have the outside, but it seems small, so. I should go to the Waverly. That's where you see a pretty rough crowd. I bet you they have beers cheaper than $3.50. Yeah. Well, they have an outside seating area too sometimes, and it's a little crazy. So anyway, you can try, you can get the download for $30, or like I said, this control systems toolbox is free. So if you want to try it with MATLAB, totally up to you. All right. Questions on how to do whole zero maps with that? Again, the nice thing is it does give you the transfer function, so you can sanity check your work.
I
Avery.
do have a question.
Oh, sorry. Go ahead, Rita.
Now, aren't we supposed to have the same number of terms in the numerator and denominator?
Yes. So
So what's up with this one?
Rita made a very good observation. Are the same number of poles and zeros shown on this diagram? So Rita correctly observed, no, it is not. So Rita, I would like to ask you to show me on a pole zero map where the pole at zero at s equals infinity belongs.
I'd have to see the original equation.
Right here. That's the transfer function. So that's the original transfer function. Where on the pole zero map would you show the zero at s equals infinity? It's a trick question. You can't, because infinity is not shown here, right? Infinity is way over here or way over here. So what we do is we say 1, 0 at s approaches infinity, right? So it's very difficult to show poles or zeros as s approaches infinity, because they don't really show up on a pole zero map. This would have to be infinity over here. So we just kind of append that, or sometimes I'll draw it like crazy high and then I'll say s equals infinity, but I'm basically breaking up the real axis. Okay.
Okay, so it is in there. It's just side
You
note.
can't display it. Yep. Avery, you had a question? Yes. So the question is, how do you go from rectangular to polar? So here's how you do rectangular. Right? You can put it at the end and it knows it if it's I. If you do it with J, I don't think it works. going on? Oh, this is hiding, I guess, 3 plus. So you can do J or I at the end and it works perfectly fine. That's how you work in rectangular. If you're working in polar, how do you enter numbers? No. It's Ferris Bueller, but Euler's identity, right? You got to use Euler's identity. So 3 times Euler's identity is E to the J theta. Quick 45 degrees. Remember, MATLAB only works in radians. There you go. So by default, it displays in rectangular mode. Okay. And you can certainly do things in polar mode, but you got to use Euler's identity, which means if I want to display this, I have to have a special display. So what I do is I do the absolute value, whoops, of the answer, I should say, and the angle of the answer times 180 over pi. That gives me 3 at an angle of 45. So you just do magnitude and angle, and you have to just write your own little script for that. Or if you want to do things and enter it in Euler's identity, it's just using the angle, but make sure it's in radians, not degrees. All right. So we talked a little bit about, I got a few more minutes. We talked about finite poles and zeros. So we're only ever going to have, sorry, not finite, infinite poles and zeros. We're only going to ever have infinite zeros. We should never have any infinite poles because those systems don't exist. So we really need to worry about these here, because we see when we take the limit as s approaches 0, our transfer functions evaluate to 0. All right. So always going to be, always, that was a very good catch by Rita. Always have the same number of poles and zeros. And why do we need to do that or include it? Once we get into root locus plots, it'll make a lot more sense. Because you can't really complete root locus plots, because I'll give you, you know what a mantra is? You say it enough time, it becomes burned in your brain. So I have a mantra, root locus, which is start at a pole, end at a 0. Start at a pole, end at a 0. So when you draw root locus plots, you have to start at a pole and end at a 0. What if you only have 3 poles and 2 zeros? Oops, I can't end, right? But you always have the same number of poles as zeros, so they always actually end. Let's see. I'll do this really quickly, I think, before we end up with there. So we have our forced response and our natural response. This is kind of a summary of what we talked about. You can see my forced response is the one that has the 1 over s, which is associated with the input. All of these 3 form our decaying exponential, and that is our natural response. So the input is the forced, the transient of the system is the natural. All right, instead of trying to jam this in, I will pause and ask any questions. We have a little bit of time. Whoops, somebody had some questions here. Sorry. If you have comments, I can't see the comment page. So feel free to say there are comments there. Oh, that's a different thing. Let me show, let's look at the lab real quick. Let's see what perhaps the issue was. We can figure it out. My fingers don't seem to work today. That was lab number 2 or number 3? This is my handwork, kind of messy. Let's go back to the actual lab. So this is modeling a first order system, right? Writing a differential equation. So all we did here was just write the differential equation, and then we did it with, you can do the summing junction, this adder, and then you can see everything in the time domain. This is a step input. This is a term, and you can see that we have to feed back this term, this parameter, because it has an impact on it. So then we just added a gain block to do it. And then what I'm showing you as I walk through, here's my input step. The output of the summing junction should be V in minus V out. But to get V out, what I need to do is I need to do one more step here, and I need to multiply that by RC, and that's equal to not V out, but the derivative of V out. I want to bring back V out, not the derivative. So I've got to integrate this to get V out, and then I can close the path. And so what the purpose of this lab is to kind of walk through each of these steps so that I can close the loop, right? That's the time domain one. And then if you did it, well, if you did it, you could also just do it. Whoops. Sorry about that. You also, what's another way to do it? Times, let's see. You could also do it that way if you did in Laplace, right? So just trying to show you, like, if you wanted to do each point, you could get it this way. Now, the advantage of doing it here is, what if I actually wanted to know what the difference in the voltages are in the time domain? I can pick off this point over here and send that to a scope, and I can monitor that intermediary point. Remember how we talked about state space, multi-input, multi-output systems? So if I want to know what's happening over here, because maybe I can make some predictive behavior, I can actually monitor that and do something with it. So instead of doing everything in one big block diagram very efficiently, sometimes it's better to do this, because I want to know, hey, what is my derivative of my voltage? How fast is that voltage changing? And can I make an assessment or an assumption on that? We can do some calculations that way. So that's kind of the reason why we did it that way. Pretty much for the rest of the semester, though, we'll probably do everything in Laplace moving forward. But tomorrow, like I said, should be fish. Okay, any questions? Everybody excited? 2 more weeks and you get break, right? After this week, it's 2 more. Anybody doing anything fun? Ah, that sounds like fun. Birthday? You doing anything fun, or are you just lamenting your birthday? Unless you're turning 21. Party with Noah on what day? March 14th. Who's gonna buy him his first beverage? Yeah, but if you go there, well, I won't say that. I'll get me in trouble. All right, everybody. Have a great day. We're out of time. Take care, everyone.